Hello, hello. Let's try. Hello. It doesn't work? Does it work? It works, right? Awesome. Welcome to the Superconducting Qubits and Algorithms Conference 2023. We're so excited to have you. So on behalf of IQM Quantum Computers, I'm too loud. Not hearable enough? Louder. Okay, I try. Louder would be good. So on behalf of IQM Quantum Computers, the TU Munich and the Munich Quantum Valley, we are liking to welcome you to SQA conference. It's really great to see all of you here. I think we have an exciting evening ahead of us. I'm still the one that needs to bother you with all those organizational details. But first, let me rehearse what the idea behind this conference was. So last year, we set out to really help facilitate our dream of making quantum computers or useful quantum computers come true. And I think last year with SQA 2022, we already went a great step into that direction. And so it's even greater to see how SQA has grown from last year. So I would like to thank all the companies that made this possible. So all those companies you see here. Thank you to Rohde & Schwarz, Zurich Instruments, Blueforce, Qblocks, Keysight, QuantrolOx, Quantum Machines, Quantware, Cruise, Coax, Intermod Products, Keycom, Oxford Instruments, FormFactor, IBM Quantum, Chatrath, Scaling Q, Classic, Uris, Hermex Systems, Kilimanjaro, Orange QS, Google, and QControl. As you recognized, a lot of great companies that actually make this happen. And of course, that's not everything. And this clicker doesn't work. That's a pity. It worked before. Also, thanks to the scientific committee, the scientific advisors for really setting the vision of this conference and the ambition for building useful quantum computers, making our dream come true. And last but not least, thank you to all of you for your participation, for the abstracts you submitted, for the talks you prepared, the posters you prepared, and just for facilitating those discussions. So we have more than 420 people coming or attending this conference, and I think this is a great achievement over last year. And now, as I promised, I will come to those very important questions. The first one are the social media hashtags. So please share the word about SQA conference, about what you see, what you experience here, what you learn here. So please use SQA conference as a hashtag, link, SQA conference, profile, and so on and so forth. And then I was asked this question now very often. Where do I actually find the toilet? So let me quickly. No, really, I got a lot of questions today, but this was by far the most common one. So in the conference guide in the app, you'll find a floor plan. And in the ground floor, there are actually toilets. They are hidden, but they are here. And speaking of ground floor, like going through the door in the middle. But speaking of ground floor, there we will have the welcome reception after our presentations today. And all those awesome booths of all those companies are down there as well. So I think we'll have a great time down there. We're now in the first floor, having the Audimax there and some lounge area outside. One floor upstairs, you'll find the poster session, another corner for food and those kind of things, and one floor above that is only accessible via elevator. That's where one of the workshop rooms is. So if you attend the workshops on Wednesday or Thursday, this might be the place you need to go to. And we have a packed agenda today. So even today, we'll have a great keynote. But first, I want to welcome on stage Stefan Filipp from the scientific committee to welcome you as well and introduce our great keynote we have today. Thank you.
So thanks a lot. Let's try this one here. This works? Yes. So thanks for the introduction. Thanks for the first welcoming words here. And so also from my side, I'm Stefan Filipp, and I'm working for quite a long time with superconducting qubits, and I'm seeing now that there's so many people here, it's actually quite an exciting time for this topic. I'm working here at the Technical University of Munich and at the Walter Meister Institute of the Bavarian Academy of Science, and I'm representing here and would like to welcome you here on behalf of the Technical University of Munich, but also of the Munich Quantum Valley, and also in terms of the scientific committee of this conference. So, unfortunately, the weather is not as bright as the days for quantum computer could be, but I promise you by the end of the week it will hopefully be better. And we'll hopefully see then also sunshine here, and I hope you enjoy also the venue. It's a pleasure to really to have this conference here in Munich, as Munich is one of a very thriving community working in quantum activities in many different projects, from quantum computing, quantum technology, quantum science, bringing together scientists, engineers, universities, research organizations, and industries, and pushing this field forward. And there's a few highlights that I want to mention here, like the Cluster of Excellence, the MCQST, the Munich Center for Quantum Science and Technology, which actually hosts a number of 50 groups working in the diverse fields of quantum foundations, quantum technology, quantum science. And that was actually paved the way towards the technology-driven Munich Quantum Valley that we are now enjoying to have since 2 years, with actually a real focus on quantum computing, building quantum computing demonstrators, and with this actually pushing the technology even further. It is between the research organizations here, the Academy of Science, the TU, the LMU, the Max Planck Society, and the Fraunhofer, and we are very happy to have now this conference. It's not only education and research that is key to this local ecosystem here, it's also the companies. You have seen some of them already here funding and supporting this conference here, and we are very happy to have this thriving environment here in Munich. It's also now the time to thank now, and giving this thank back to IQM, to Stefan Seegerer and then the team, and also to the whole IQM company in actually initiating this conference, bring this to life, and providing now a place where we can discuss and fill quantum computing, fill this with life and activity, and bring this forward. So thanks a lot to this initiative here, which I think will become a very fruitful discussion event. Thanks a lot also to the organizers, Stefan Seegerer, Klaus Liegener, and the team that has actually helped in setting this up. And lastly, thanks to all of you for joining this event. We have already heard, we were excited by the many applications that we have, by the many contributions, and we are now looking forward to many exciting talks in the next days to come. With this, I want to hand now over, after a little bit of introduction, to Shruti, who should be now joining me here on stage. So as our first keynote speaker, I want to welcome here now Professor Shruti Puri from Yale University. Shruti actually received her PhD in applied physics at Stanford University in 2014. After then, she conducted a postdoc research with Alexandre Blair at the University of Sherbrooke, and from then moved them to Yale University as a postdoc with Steve Gerwin, and then stayed there and became professor, and where she's heading now the group and working on quantum theory in a very broad sense, quantum optics, quantum control of open quantum systems, quantum algorithms, and quantum error correction. She has pioneered quantum information processing based on Kerr-Cat qubits that are based on microwave photons, and how they react to noise, and how we can use this actually for quantum computing. And so I'm happy to hear, and that's probably also this good starting point, happy to hear more about this topic. And so please, Shruti, the stage is yours. Thanks for coming, and please.
Does this work? Awesome. Firstly, thank you for the invitation to the organizers. I'm very excited to be here. This is actually my first trip to Europe since the pandemic, so it's been interesting. All right, so this is my group, and before starting my talk, I would like to acknowledge all the students. It's really their hard work that has resulted in some very nice new results. The results that I'll be showing today are mostly with collaboration with Jeff Thompson's group, and in my group, my postdoc Jehan. The pointer is not working. Well, okay, my postdoc Jehan and my grad student Kavya are the lead for these results. Okay, so what I want to talk about today is more generally about how should we think about making good qubits and making good error-correcting codes. So when somebody gives you 2 qubit systems, one of them has a higher qubit system A has a higher fidelity than qubit system B, which one is better? You would naively answer that, well, since qubit A has higher fidelity, that is a better qubit to use. But I think the answer is more complicated. You should not just look at this one number fidelity, but you should ask yourself, what is the structure of noise in the system? Where is this infidelity coming from? Because some type of errors are easier to correct, and some types of errors are hard to correct. So this is kind of the hierarchy of errors from easy at the top to the most difficult one. So the most easy type of error to correct is erasure errors. So what is an erasure error? The first type of erasure error is what we call the standard erasure error, where your qubit 0 or 1 can leak to a new state. Let's call it E. And you're handed a flag. You're either able to do a measurement, or the experiment has a way to tell you that this transition has actually happened, that something has gone wrong with your qubit. This is a standard erasure error. You don't know where, if you went to the state E, it could have come from the atom starting in 1 or 0, but you know something bad has happened. There's also something called as biased erasures, where you go to the erase state only or mostly if you start from the 1 state. So if you see the flag, you know that the atom must have started in the 1 state. So biased erasures are much easier to correct than standard erasure errors. The most common type of error that we think about is polynoise, which is the action of poly x, y, or z operators on your state with some probabilities, some arbitrary probabilities. A general depolarizing polynoise, where all of these 3 different types of errors are equally likely, is hard to correct. If you have biased polynoise, so if one of these errors, say the z error, is more likely than the x or y errors, we say we have biased polynoise, and a highly biased polynoise channel is easier to correct than an unbiased polynoise channel. Of course, the most difficult form of error is leakage. This is as if you had an erasure, but you don't have the flag. So your qubit leaked to some different state, and you don't know about it. Leakage errors are notoriously hard to correct. They spread rapidly through circuits, and so on. So just don't give me one number. You should think about the entire structure of noise in the system. Let me expand on this a little bit more. So let's look at polynoise. If you have some number of qubits, on each qubit you have IID polynoise with probability of x errors as px, y errors as py, and z errors as pz, then you can show that the achievable capacity, like if you make an error-correcting code, what is the capacity you might be able to get? That's the achievable code capacity, is given by the hashing bound, which is 1 minus the entropy of noise. So that means lower the entropy of noise, higher is the capacity. So if the probability of errors is too large, then this quantity in red is large, and the capacity can actually become negative. That means that's bad. If the probability of errors becomes smaller, the entropy becomes smaller, and this quantity becomes positive. That means you can get positive error correction code capacity. The value of the errors, the probability of errors, when this quantity becomes exactly 0, is like the threshold for error correction. That is the best threshold you can ever achieve, and that's called code capacity threshold. So I can calculate the code capacity threshold as a function of bias in the noise. So bias is the ratio of z errors to x or y errors. And so as the bias increases, this code capacity threshold increases. The total error rate is constant. P1 plus Px plus Py plus Pz is the same, but this quantity entropy is different for different biases. So again, this is telling you that a code capacity can be much higher if you have bias noise. Let's now look at something called the erasure error, right? Let's look at the standard erasure error and the biased erasure errors. In this case, we actually know exactly what is the code capacity, not just like an achievable bound. In this case, the code capacity is 1 minus 2 PE, where PE is the probability of erasure, in case of standard erasures, or 1 minus PE in case of biased erasures. So you already are seeing that biased erasure has a higher capacity than the unbiased or standard erasure. And the value of P for which the capacity becomes 0 is actually half in case of erasure and actually 1 in case of biased erasure. Again, telling you that the thresholds increase if you go from standard erasure to biased erasure. Now, you can have a noise channel where you have both erasure errors and poly errors. So you can define a erasure fraction, which is the ratio of erasure errors to total errors in the system. So basically, it's saying how much of total errors is your erasures. So in this case, you can again calculate the achievable capacity as a function of this erasure fraction RE. So at RE equal to 1, as expected, for the biased, the blue line is for biased erasures, and the red line is when the erasure is standard, so unbiased. And again, at RE equal to 1, that means all errors are erasures. You get the threshold of 1 for biased erasures and threshold of half for unbiased erasures. But as you see that as RE increases, these thresholds increase. And these are much higher than the thresholds you could have achieved in case of polynoise. Again, this is explaining that triangle to you, that in terms of thresholds, going up, being up in that triangle is better. You can get higher thresholds. Okay. Another interesting property of erasure errors is that if you have an error correcting code that can correct for some number of poly errors, you can correct for twice as many erasure errors. So you basically get more bang for your buck. Let me now explain this further with some examples. So let's look at a simple example of repetition code. Repetition code where the stabilizers are, this is a 3-qubit repetition code with the stabilizers x1, x2, and x2, x3. And this is going to correct for Z errors. So this is, you have an arbitrary superposition of your repetition code states. Suppose there was a Z error on the first qubit, then the state that you get is on the right here. I can't see the, never mind. So you get that state there. And if you measure the stabilizers, you will get x1, x2 to be -1, and x2, x3 to be +1. So if you measure the stabilizers and you get these outcomes, you know that a Z error happened on the first qubit, and you can go correct it. Now, there's actually another way in which you can get this same measurement outcome, which is that if 2 Z errors happen, if Z errors happen on Z2 and Z3, on the second and the third qubit, they give the same measurement outcomes. However, if you're assuming IID polynoise channel, then since the probability of 1 Z error is more likely than probability of 2 Z errors, whenever you see this measurement outcome, you should assume that it came from 1 Z errors. So in this case, the probability that you have failed is the probability that actually 2 Z errors happen, and that's p squared. And so you've done better, right? You've reduced your logical error rate quadratically. In general, for an n-qubit repetition code, you can correct for n-1/2 Z errors. You can calculate what the logical error is. And you can show that if the probability of Z errors is smaller than half, then the logical errors will decrease exponentially with the size of the code. Again, this just simple formula will tell you what the threshold is. Great. Now you can let's look at if you had biased erasures in your system, and now let's look at how this repetition code behaves. So you start with the repetition code state, and say the first qubit got erased. So you have 3 different flags. Each flag is shown with a different color, which says that if the first qubit is erased, you know that it was the first qubit. You don't confuse it with the second or the third qubit being erased. So you have perfect distinguishability between erasures. So if the first qubit is erased, this is the state, and you get your flag. So you replace the erased atom with the fresh atom prepared in the 1 state. Because it's biased erasures, you know that the atom came from the 1 state, so you just put it back in the 1 state again. So this is the state you have. And if you note, this state over here comes from this state by the action of the operator identity plus Z1. So if I apply identity plus Z1 on this guy over here, I get the second, I get this state at the rightmost point. Okay, so now this is superposition of identity or Z errors happening on your repetition code state. Now you go and measure your stabilizers. You will either get +1 outcome, or you will get -1 outcome. If you get +1 outcome, that means you know you have projected your state as if identity happened. If you get the -1 outcome, you know you have projected your state onto as if a Z1 has happened. In this case, there's no confusion between did Z1 happen or Z2, Z3 happened. Because I know that the first qubit was erased. The qubit number 2 and qubit number 3 were not erased. So unlike in the polynoise case, where there was a sense of confusion, there is no sense of confusion in case of biased erasures, because you know it was only the first qubit that went wrong. So in this case, the probability of, so the only way you've lost your information is actually if all the 3 qubits are erased. If all the 3 qubits are erased, the superposition state decomposes into this state over here, and there's no way for you to recover information. So the logical error rate here is the probability that all 3 qubits got erased, and that's p cubed. And in general, for a n-qubit repetition code, this will be p to the n, the logical failure rate. So clearly, if p is smaller than 1, by increasing n, your logical error rate decreases exponentially small, so the threshold is 1. Also note that the logical error rate decreases faster, goes as p to the n in erasure case, rather than p to the n plus 1 over 2 in the poly case. So this is basically demonstrating that if a code can correct for t poly errors, it will correct for twice as many erasure errors. Good. Now, let's contrast this with the case when I have unbiased erasures. So in this case, when an erasure happened, you get, so suppose the erasure happened from the 1 state. You get the state on the right here. But you cannot distinguish it from the erasure happening from the 0 state. When you get a flag, it's not a different flag for erasure starting from 0 state or erasure starting from 1 state. Because of which, you don't know if the state, what the superposition state was on the right. You don't know whether the superposition changed from x plus y to x minus y. So unbiased erasure, you can see that is introducing an extra x-type error in your system. And my repetition code cannot correct for both z errors and x errors. So in this case, repetition code is not enough, and I need to go to something different than like a surface code. However, I don't have time to go into the details here, but you can actually show that using arguments from no cloning theorems and so on, you can show that the threshold for unbiased erasures will be half. Okay. Nonetheless, the unbiased erasures still have the property that the logical error rate will decrease quadratically faster compared to if you just had polynoise. So like in the surface code, if you just had standard erasures, the logical error rate also decreases as p to the n rather than p to the n over 2. Okay. Now, let me first say something about what are these requirements on these flags that you have for erasures. You might want to, like, to check whether the atom was erased or not, you might actually need to do an experiment, apply a pulse or something to get this flag. This flag necessarily must be so that your measurement is QND. That is, if the atom was not erased, this process of trying to get the flag should not introduce new errors in your system. If you do that, that's bad. So your way to get this flag must be QND. This is also called as mid-circuit erasure detection in papers if you have seen them. You should also have a good spatial resolution. Like I said, you necessarily needed to know that the erasure happened on the first qubit, not on qubit number 2 and 3. So you need to have good spatial resolution. In case of circuit level noise, you need to also have good time resolution, like at which point in time did your atom get erased. False positive, like erasure didn't happen, but you actually thought it actually happened, is fine. It's less bad. It's basically you would preemptively replace the atom even if it didn't get erased. That's not so bad. It's just some additional erasure error. False negative is actually bad because that amounts to leakage error, that the erasure happened, but you missed it. That's a leakage error. And in some cases, it can also introduce poly errors. And the way to correct for leakage errors is we can't directly do it in the stabilizer formalism. You have to do measurement-based error correction or teleportation-based error correction to actually deal with leakage errors. You can deal with it. It's just more costly. OK. So let's talk about, with this kind of background, on why it's important to look at the structure of noise and why these erasure errors are so important. Let's look at if we have some qubits where the dominant errors are biased erasures, right? Biased erasures seem to be like the really good type of noise to have. So the first qubit platform in which we found that noise could be dominated by biased erasures was this neutral atom ytterbium qubit. This was work done in collaboration with Jeff Thompson's group at Princeton. So here the qubit is encoded into metastable states of the atom, not the ground state, but the metastable state. So it's still a long-lived state. And when the atom is sitting in the metastable state, it doesn't really decay. I mean, it does decay, but the coherence time is long. But two atoms don't interact with each other when they're in the metastable states. To have them interact with each other, you have to excite the atoms to the Rydberg state. And by putting two atoms next to each other in an optical lattice, if you excite both of them to the Rydberg state, you can get 2-qubit control-Z gates. Now, the main source of errors is coming from the 2-qubit control-Z gates, because when you excite the atoms to the Rydberg state can actually decay. The Rydberg state can, for example, decay to the ground state. If you have a way to tell that this leakage has happened, then you convert this error to an erasure error. And you can do this by applying an additional laser pulse and seeing the response. Like you can do fluorescence measurement and see if the atom went to the ground state or not. So this is called erasure conversion. More importantly, this pulse doesn't disturb the atom, doesn't cause any back action if the atom was in the metastable state. If it went to the ground state, it will tell you that, hey, it will emit some light, and you know that something bad has happened. But if the atom is in the ground state, you won't see anything. The atom's not disturbed. There is no back action. So this is truly like a QND erasure detection. OK, so like I said, the main source of error here is coming from erasures during the control-Z gates. So after you do the control-Z gate, what you will do is there's a chance that one of the atoms went to the ground state or leaked to some other state. You can apply this extra pulse to detect if this leakage happened. And if you see that, yes, indeed, the atom went away, you can replace an atom back in the one state. And like I showed in some of the previous slide, replacing the atom back in the one state is like either an identity error or a Z error, right? It's a superposition of I plus Z. OK. So the dominant source of errors in the system is biased erasures. sorry, the animation got a little bit messed up, but yeah, so the error channel of the native control Z gate in the system is either identity or a Z error. With lesser probability, if there was no erasure, there's still some chance that there was a poly error, right? Which could, for example, come from decays within the qubit subspace. But that happens with much less probability. In the system, we estimate that the erasure fraction could be as high as 98%. Recently, the erasure conversion, the QND mid-circuit erasure conversion for this system was also demonstrated in Jeff's group. The erasure fraction was smaller than 98%, but it's a first experiment. We are very confident that we'll get better numbers. OK, great. Now, with this erasure conversion idea, many other platforms started to look deeper into how they can make new types of qubits, where the dominant errors are erasure errors. And one of the platforms was indeed the superconducting circuits, in particular these bosonic superconducting qubits. So one of the very nice proposals is this dual rail qubit architecture, which Patrick is going to talk about more tomorrow. So the idea here is that you store a qubit in a single excitation distributed between two high Q oscillators. So whether if the single photon lives in one of the resonators, it's qubit state 1. If it's in the other state, if it lives in the other resonator, that's qubit state 0. Now there's all the gates, single and 2 qubit gates, happen with a beam splitter type interaction and the Anna-Josephson junction. I'm not going to go into these details here. Patrick is going to talk about that tomorrow. This is just one slide on superconducting qubits because this is a superconducting qubit conference. OK, so yeah, so all the gates, basically the main gates, the 2 qubit gates, happen by interactions with the transmon. In particular, we use a 3-level transmon, GEF, 3 levels in the transmon. And the gates are designed such that the flag is essentially the state of the transmon, which state the transmon ends up in after your operation. So if the transmon ends up in the G state, everything is fine. But if transmon ended up in anything but the G state, then something went wrong, and that was an erasure. Recently, some preliminary erasure detection ideas were demonstrated also for this dual rail platform in this system. There's also work by Amazon on both the theory and the experiments of dual rail type qubits with only transmon, no resonators. There are one of these references over here. They also have experiments. So if you're interested, please see those papers as well. How much time do I have? 10 minutes, OK, great. 20? 20, OK. I'll take 20. OK. So far, I have shown you what are some nice noise properties. But now we also need to think about what codes. Can any code be used to get high thresholds against this noise? Well, the codes need to have the right symmetry to be able to give you high thresholds or low overheads for this specific noise channel. So let's look, for example, at the standard CSS surface code where you have 2 types of stabilizers, the X-type stabilizers and Z-type stabilizers. And let's look at the XZX surface code where you only have one stabilizer, which is this 4-body XZX operator acting on the 4 qubits around each plaquette. Now, in the standard surface code, if you have Z errors, let's just look at Z bias noise. So if you have Z errors, then it can create syndromes that go vertically up or down. But if it's on certain qubits, the syndromes can happen left to right. So a Z error creates syndromes up and down and left and right. So it creates syndromes in 2-dimensional planes. In the XZX code, if a Z error can only produce syndromes that go in the line. They're disconnected lines. Syndromes, so these are 1-dimensional syndromes. one-dimensional syndromes are easier to decode than two-dimensional syndromes. So the XZX code has the right symmetries to efficiently decode Z errors, and so it can actually show improvement in thresholds when you have Z-biased noise. In fact, the XZX code reduces to the repetition code for infinitely when you have just Z errors, no X or Y type errors. So this paper, this plot is from this paper which introduced the XZX surface code. And it actually simulates the code. And so the black line here is the threshold predicted by the hashing bound. And the dots are the actual numerical simulations. And so you can see that the XZX code threshold follows the hashing bound. And in fact, it can actually do better. Remember, hashing bound is just an achievability threshold. You can actually do better. So the XZX code actually does do better than the hashing bound for some values of the bias. And it's actually very hard to do some better than the hashing bound. The CSS code, on the other hand, because it doesn't have the right symmetries, it actually starts doing worse as the bias increases. So this also tells you that the code needs to be tailored to the noise that you have. The XZX code has the right symmetries to efficiently correct bias noise, and it also actually efficiently corrects biased erasures, or noise channel where you have both erasures and polys. It follows the hashing bound in both the cases. The other nice thing is that if you have high bias, what you can do is you can change the aspect ratio of the lattice you're using. So the number of Z errors you can correct depends on the length of the lattice. The number of X errors you can correct depends on the breadth of the lattice. So if you have highly biased noise, and you can choose dx, the breadth, to be smaller than dz, so you can save on the number of qubits that way. In particular, for dx equal to, so for bias of infinite, you can actually just use dx equal to 1. And so this basically just becomes a single line of the repetition code. OK, great. So when I'm talking about all these codes, I've not actually told you how you're going to implement the code. You need to also think about what happens in the fault tolerance setting and whether these symmetry properties are preserved when you actually start doing gates and so on to measure these stabilizers. OK, why this may be a problem will become clear from what I'm going to talk about next. So let's look at the surface code with biased erasures. Okay. So how do we measure the stabilizers? We're going to put an unselect qubit at the center of each plaquette and do a bunch of control Z and control NOT gates between the unselect and the data qubits, and then measure the unselect qubit to determine what the value of the stabilizer was. So the control Z gate we have already looked at. So like I said, what you do is you apply an erasure detection pulse after every control Z gate. If the atom was erased, you know from your pulse response that it was erased. You replace the atom in the one state, and the resulting, the net effect is that either an identity or a Z error happened on that particular qubit. In the C0 gate, however, you do the same thing. The way we do C0 gates is we sandwich the C phase gate between two Hadamards. That's the native gate available in these atoms. So now if you apply your erasure detection pulse after the control Z gate, and you see an erasure, and if you replace the atom with the one state, then after the Hadamard, you get the Z error is converted to an X error. So the noise channel of the C0 gate is either identity or X happening on that qubit. So while the noise channel of the C phase is identity or Z, the noise channel of the CX is identity or X. So your noise channel is no longer biased. Your Z errors are being converted to X errors. So it's no longer biased anymore. So will you get any advantage now? Turns out the answer is yes, which was remarkable. I didn't believe that the answer could be yes, but Jeff Thompson overruled me and was like, no, let's do the simulations. And indeed, we do see an improvement. So the blue line is when the blue dots are when I have unbiased erasures, that is the standard erasures. And the orange dots are when I have biased erasures. I clearly see an improvement when I go from standard erasures to biased erasures. The threshold improves almost by a factor of 2. So if you have an erasure fraction of 98%, which is what we would expect here, the threshold is about 8%, rather than a threshold of 4% for this blue star over here. Now, it turns out, well, not surprisingly, that this advantage, the advantage of this orange dots, also happens if I just use the CSS code. Because I'm actually not using the symmetry properties of the code at all. The symmetry properties of the codes was this one-dimensional syndromes that you get when you have Z errors. But now because I have both Z or X errors, there's no longer one-dimensional syndromes. You have two-dimensional syndromes. So even the CSS code actually shows the same improvement in the threshold. If suppose, magically, someone gave me a CNOT gate where Z errors did not convert to an X error. Suppose magically I had a bias-preserving CNOT gate. Then the XZX code will actually do much better. Then you get these green dots, and you'll actually get a better thresholds. But more importantly, because you're not converting Z errors to X errors anymore, you can get away by using the asymmetric lattice. Like you can make DX smaller than DZ. In particular, say if RE was 1, right? If you have infinitely biased erasures, there's no polynoise, just biased erasures, then you should get away by just using a repetition code. If you don't have a bias-preserving CNOT gate, Z errors convert to X errors, you cannot use a repetition code anymore. You have to use a square code. If you had a bias-preserving CNOT gate, you would be able to use a single line of repetition codes and save on the number of qubits. So this is demonstrating that it's not just the code, but how you implement the code that's important in really taking the advantage of noise. So the question that we asked was, is it possible to make the repetition, just let's take the example of RE of 1, so only biased erasures. Can I get away by using a repetition code even without a bias-preserving CNOT gate? The answer turns out to be yes. You can get away, but you have to do something clever. You can't work in the circuit-based model of error correction. You have to go to a measurement-based model of error correction. Because I don't have a lot of time, I can't go into a lot of details. I'm going to just stick with the repetition code example and give you an intuitive picture of how one would implement error correction in the measurement-based model. OK, so first thing I need to know is teleportation and Bell measurements. So suppose I have a qubit, state psi, and if I want to teleport it to some other qubit, I might prepare a G at Z state like this. And I'm then going to do a fusion measurement, but that is a measurement of XX and ZZ operators on the first two qubits. This measurement can be destructive, can completely destroy the qubit, I don't care. I'll measure the first two qubits in the Bell basis, and I'm going to measure this qubit just like in the X basis, an X measurement. And as a result, I would teleport this input state psi to the output qubit over here, which I have not measured, up to some poly corrections, which depend on the measurement outcomes. So if the measurement outcome of ZZ was 1, I apply a poly X to the state. If the measurement outcome of XX was 1, I apply a poly Z to the state. So specifically, what happens if I have errors in the system? Any error can be reduced to measurement errors. Even if you have gate errors, at the end of the day, I'm going to measure the qubit, and all errors are converted to measurement errors. So I only need to think about measurement errors. A Z measurement error will only apply an incorrect X to the state, and an X measurement error will only apply an incorrect Z to the state. Now, suppose you have your physical noise is Z biased, then physical Z errors will only affect X measurements. Right? A Z error cannot affect Z measurements because it commutes with Z measurements. So physical Z errors will only make unreliable X measurement outcomes. And so that means a physical Z error will only ever apply a Z error to the state that's being teleported. So now all I need to do is, while I am teleporting this state, can I correct for Z errors? So now, basically, can I implement a repetition code as I teleport some states of the qubits? Suppose these are my starting states, and I wanted to implement repetition code. So that means I want to measure XX correlations between these qubits. And I'm going to do this as I teleport these states. So like I said, I just put these G and Z states as shown, and I can just perform fusion measurements and single qubit X measurements and teleport my state from this input layer to the last output layer. But now, as I'm teleporting, I also want to measure this XX. So before that, yeah, so these fusion measurements and X measurements just teleport your state. Now, if I want to measure X information as I'm teleporting, I'll just add these bridging regions, these bridging qubits in the center. So instead of teleporting with 3-body G at Z states, I teleport through 8-body G at Z-like states. And the measurement outcome of the X measurement outcome of the center blue dot qubits actually is measuring XX information in time. So the first line is like a repetition code at time t0, and the second line is a repetition code at time t1, and so on. So after this measurement, the input repetition code has been teleported to the output qubits that you have not measured, and you have got the XX measurements in between. This is the 8-ring resource state. I was trying to explain from this figure what this state is without actually writing, the bra and ket notation, because it gets really complicated. But because I have only 5 minutes, I will not do that. Basically, you can now just repeat this over and over, this cycle over and over again, and you are basically implementing repetition code. This is just implementation of repetition code with measurements. So now you see, if I'm able to prepare these 8-body states such that the dominant errors are Z, and if I'm able to do the fusion measurements such that only the X part of the measurements are incorrect, then I'm done. Then I can implement this repetition code without converting Z to X errors. So state preparation is actually very easy. So let's look at, imagine our atomic setup. So you prepare all the atoms in the plus state, you do your control Z gates, you do your Hadamard gates as shown, and after all of these gates, you apply your erasure detection pulse. Remember, the Hadamard gate was converting an erasure error to the X error, right? So I'm still using Hadamard. What am I doing differently here? Well, I just don't use the state if I see an erasure. I post-select out. So I never pass the states which had X erasures into my repetition code. So using post-selection, I'm getting rid of this problem of Z errors being converted to X errors. The final element is how do you do these fusion measurements? So the circuit for that is shown over here. You have qubits I and J on which you want to do the measurement. You put an Ancilla qubit at the center. You do control Z gates, like shown. You measure the center Ancilla qubit in the X spaces. That tells you about the ZZ, that effectively measures ZI, ZJ. And then you just measure qubit I and qubit J independently in the X basis and multiply the measurement outcomes. You get the XX measurement. So this is destructive measurement. That's fine. I don't have to ever reuse these qubits again. I don't care if these measurements are not Q and D. And in this case, you can show that if any qubit was erased, say the Ancilla was erased, I can just stop my circuit and go measure each of the qubit in the Z basis. So if I see erasure anywhere, I can measure each of the, stop the rest of the circuit, measure qubit I and qubit J in the Z basis, and multiply the outcomes to get the ZZ measurements. So even if there's an erasure, I can always recover ZZ. I will never be able to recover XX, but I'll always be able to recover ZZ. So this is what we call a bias-preserving fusion circuit, and combined with the state preparation circuit, now I have all the tools available to me to actually implement the repetition code if I just have physical z-biased erasures. You can use the same principles to do an XZZX code where you can correct for all type of errors X, Y, Z. I tried to explain how you do that here. Not super important. I can just give you the result. So this is a result of measurement-based simulation of the XZZX code. We get the threshold as a function of the erasure fraction. We get, as expected, this threshold increases. And this actually does much better than the circuit-based approach. In particular, for this red star, when erasure fraction is 98%, the threshold is 10.3%, which is higher than the 8% we saw in the previous case. This is a comparison of different regimes. So if the erasure fraction is 1, compared to the circuit level approach, we get a threshold of 14%, whereas in the circuit-based approach, you would only get a threshold of 10%. Because this preserves the Z nature, again, I can implement a rectangular XZZX code rather than a square XZZX code and reduce the overhead requirements. So, summary. When you think about good qubits, think about what is the noise structure, and when you think about making good codes, think about the symmetries of the code and how you preserve them when you actually do circuit-level simulations. That's it.
Thanks. Thanks a lot, Shruti, for these very insightful talks in the art of error correction and how to choose the right qubits. Please, the board is open for discussions and questions. So I would have one first question. You mentioned in your atomic experiment that if you have an erasure error, then you can easily, or it's easier to correct for that, basically. And then you mentioned that in the qubit subspace, there might still be some other errors, which you then, okay, assume that they are small enough or so, but what if they are not small enough? Do you have to implement a hierarchy of error correction codes, then correcting for each layers of your pyramid of errors, or how should I imagine this?
So if I use a code like the surface code, it can correct for all errors, erasures or poly errors. So in principle, you don't have to have errors in the computational subspace small, but if you have them smaller than the erasure errors, then you'll just do better. So you want to design qubits such that the dominant, you're able to tailor the dominant error channel to be erasures. So suppose in the atomic case, if I had chosen to encode the qubit in the ground subspace than the metastable subspace, then the decay, the dominant channel was decay from the Rydberg state to the ground state. That error now becomes a computational basis error, not the erasure error. Now by choosing to change my qubit encoding, now I'm going to encode my qubit in this metastable state where the Rydberg atom, where the Rydberg state doesn't decay much. The Rydberg state mostly decays to the ground space. So now I've reduced the computational error. I've not reduced the erasure errors. The erasure errors, I've changed the nature of error. The total error remains the same because the rate of decay from the Rydberg state to the ground state is the same. But I've changed the nature of error by choosing how I encode my qubit.
Okay, thanks. Further question?
Thanks, that's a great talk. So some of the earlier work on erasure and Pauli errors requires adaptive stabilizer measurements. Do you consider the sort of overhead of doing those adaptations in real time?
Sorry, can you say that? Sorry, it's a bit echoey, I can't.
So if you have erasure errors, one way to think about that is that you need to adapt the stabilizers that you measure to account for the fact that some of the qubits are no longer available. And so do you take account of that adaptation that you need to do in real time?
That's a very good question. I should have put a backup slide there. So at the moment, on all these calculations, we are assuming that as soon as I see an erasure, I put the qubit back in. If I don't do that, like if I don't have the ability to immediately replace the qubit, the erasure is going to kind of spread. That error is going to spread, and it's going to affect these numbers. And I have some plots to show how it affects. like in the surface type code, if we say that you don't, if you're unable to replace up to like 2 gates or something like that, then the threshold reduces by half, roughly. Yeah.
Okay, here's another question.
Thanks for the great talk. So you said that when you're looking for these like erasures, where you're looking for flags, so these measurements for the flags, you said they have to be QND. Is there any threshold for that? So does this have to be completely QND, or can you accept some amount of QND errors?
Of course, nothing is completely QND. There's always going to be some back action. So that will, depending on what kind of back action it is, it will maybe introduce additional poly errors, you know, or something like that. So you can account for the ineffectiveness of your QND measurement in your simulations, yeah.
Please, any further questions? I don't see any. So then, thanks again for the great talk. And we are moving on to the next point in the program. Stefan, you're taking over.
We had an awesome keynote by Shruti. Thank you for that. And before we go into the welcome reception, we have some great announcements that are still coming up. And for this, I would like to welcome first on stage my dear colleague, Björn, who will share something about up-to-date stuff from IQM with us. Please, Björn.
Okay. I'm not sure what is the best way to move forward here. Right, yes. Well, okay, the picture is good. So I'm very excited to be here at TU Munich in Garching. I arrived in Munich roughly 20 years ago to do my postdoc at the Max Planck Institute for Physics in Freimann. And we had a lot of good interactions with the theory group here in Garching, so I'm really excited to go back here because it reminds me of these exciting times when I was trying to push forward the boundaries of high energy physics. So I really feel the scientific spirit back being in this audience here. I think what we can say is that quantum computing has made enormous progress in the last years. Not only on the scientific side, but also on the economic side. So we see that we have a lot of prospects and positive signals from the industry that industry really wants to use quantum computing to solve their use cases and problems. But obviously, we're not there yet. So the path to universal quantum computing or error-corrected, fault-tolerant quantum computing is long. And there is a lot of research to be done, a lot of discoveries to be made, maybe even breakthrough discoveries. And what we will need for that, on the other hand, is talent. So we need education, training, and we need this on a very broad basis. And we as IQM have thought about how can we contribute to that, how we can enable that this kind of research and talent acquisition education will contribute. So we came up with the idea of having a very simple system that we call IQM Spark. So let me introduce to you IQM Spark, a turnkey solution for quantum research and education. And the idea we have for the system, the main feature basically is that we have a very affordable system, a 5-qubit system, which allows you to have a hands-on experience with a quantum computer. It's a turnkey solution, so it's ready to be used for computing, but it is an excellent complement to the cloud access that is available, or also to simulators, because as we all know, real-world equipment really behaves differently than, let's say, a simulation or also computing resources that you use. So I think this is really an excellent complement that allows you to build up your own labs with a solution that is ready there. But you can start use it for bachelor and master education of bachelor and master students. But you can also start defining interesting research and go further into PhD students or postdoc development and probably come up with your own interesting research. It comes together with a education package that some of you already might know from the IQM Academy. And I think this is a very nice package that will exactly bring forward education and research and put it on a broad base. So I think this is exactly the right audience to discuss this. So please, if you're interested, reach out to our colleagues, ask the expert, come to the booth, and we will be very excited to get your feedback about this idea and discuss it with you in the next days. So thank you for this, and I wish you a very excellent scientific conference, and with this I'll hand back over to Stefan. Thank you very much.
Great, thank you. And I know that we're all looking for this welcome reception we have downstairs. And the good news is there is an open bar. And the reason there is an open bar is because we have great companies that make this possible. And we now want to welcome on stage Yonatan Cohen from Quantum Machines, who has some exciting updates to share with us as well. And please, I need to say that Quantum Machines is with SQA from the beginning, so we're glad that you're back and you actually have a great announcement to make today. So please, Yonatan, the stage is yours.
Thank you. All right. We all want useful quantum computers. This is probably the biggest goal that we all commonly share together here in this room, here in our community. So can we make this future come sooner? Can we make faster progress? At Quantum Machines, we made it our mission to accelerate the realization of useful quantum computers. But building a useful quantum computer is a very difficult task. And we believe that this is not going to be achieved by a single group or a single company. This is really a worldwide community effort. It's a worldwide community effort, and we're all in this together. And so for us at Quantum Machines, this mission of accelerating the realization of useful quantum computers really means to work together very closely with this amazing community and to provide it with the technology and the tools that will allow everybody to make faster and better progress across the board. In 2019, we launched our first product, our first quantum controller to the market. And we believe this brought a paradigm shift, a shift from using general test equipment, specifically arbitrary waveform generators and digitizer to control and measure quantum devices, to a new approach, what we call the pulse processor approach, where the entire quantum control and measurement sequence or program runs entirely from a dedicated processor that we call the pulse processor. This allowed to have a single quantum controller that is very easily, very intuitively programmed, while providing unprecedented runtimes, as well as opening up the way to new possibilities such as mid-circuit measurements, real-time classical processing, and ultra-low latency feedback. So this was our first platform, the OPX platform. And since we started, we grew quite significantly, we believe because of this paradigm shift, where today we have over 250 customers across the globe, with more than 150 employees in the company. And most importantly, and the thing that makes it really the best part of it all, that makes this hard work pays off, is that our customers are succeeding to make great impact on the field. So what's next? Well, we are ready to tackle the next industry challenges, and we identified two major challenges that need to be addressed. The first one is to scale up the control system, scale up to a control system that can provide, that can control 1,000 qubits and beyond, while still keeping the capabilities that we introduced with the OPX platform. And the second one is to push fidelities to new limits. And here we believe that it's very important to optimize the analog specifications of the controller to the specific needs of quantum control. So we've been working very hard on these two challenges for quite some time. And today we're very proud and very, very excited and thrilled to share with you for the first time the launch of our new flagship product. All right, dramatic. Yes, very dramatic. So this is OPX 1000. It's a massively scalable quantum control platform. The basic unit is a 3-unit rack chassis that can host up to 8 front-end modules, pluggable front-end modules. We call them FEMs. And the first FEM we're launching today has 8 output channels and 2 input channels, which makes for the highest density available today in the market in terms of channel density of control signals. Then multiple multi-OPX chassis could be stacked together, connected together, with extreme synchronization and data communication across all the system, so that it all behaves as a single controller that can support almost 1,000 channels in a single rack. And of course, multiple racks could be used. This is then combined with state-of-the-art analog performance. For example, increased sampling rates and bandwidth, ultra-low jitter, and extreme phase stability, increased voltage ranges, and many more. State-of-the-art low-frequency noise, and many more features. And again, this is all while keeping the OPX-ness of the platform with the pulse processor approach, with the real-time classical processing, real-time measurements, real-time feedback, and the intuitive pulse-level programming with our programming language QuA. And finally, we also made a lot of efforts to make this system what we call data center ready, with, for instance, hot swappable critical components and redundancy of single point of failure elements, as well as multi-user support and parallelization support. And finally, and very excitingly, soon, the integration with the NVIDIA GPUs, a product that we call DGX Quantum, that we're working on together with NVIDIA, and we believe is going to be an important next step in integration between classical and quantum computing. So this is the OPX 1000 platform. We hope that, like the leap we made in 2019 from AWGs to the OPX, the pulse processing approach, we hope that we're ready now to make the next big leap from a lab controller to what we call data center ready controller or infrastructure. And most importantly, we hope that with this product, with this new platform, we can support you and our community to make faster and better progress towards the future of the field. So with that, let me thank you. I want to thank the organizers for setting up this conference every year. This is an amazing opportunity to come and meet everyone, and I'm very excited to meet everyone in chat. Thanks.
Thank you, Jonathan. I think you mentioned the most important part of SQA conference, which is really bringing the community together. And speaking about this, so Quantum Machines was one of the first believing in this idea, but actually the first to believe in was QuantrolOx, and Vishal is here to share something with us about what it's new from their side. Vishal, please, the stage is all yours.
So a very good evening to you. It's been a long day. We at QuantrolOx, we automate quantum computers. And after the announcement from Quantum Machines, we hope very soon to automate 1,000 qubit quantum computers. Starting off, what do we do? Our history and our roots are from the University of Oxford. We spun out in 2021, and the work on which the company was founded goes back to some of the groundbreaking work done by my co-founders, Dr. Dominic Lennon, sitting there, Natalia Ares, and also Professor Andrew Briggs. And the focus of the research was automating the tuning and optimization of qubits, specifically silicon and spin qubits, using machine learning. When we talk to experts around the world, what experts are in agreement that to make practical quantum computers, we will need a few 100,000, or in certain cases, even a few million qubits to be in a constant state of tune. But the problem that we have, that right now, with the control methods that we have, you typically need 3 to 4 experts to constantly intervene to keep the quantum computers operational. And given that it takes 30, 35 years for a quantum scientist to gestate from the time they are born, and so it's definitely not something that will scale. So what do we do about it? When we also talk to the labs around the world, among the various bottlenecks that we have for scaling of quantum computers, one of the ones that we hear most often is that the tune-up times take long. A few months ago, in June, I was in South Korea and speaking to Professor Yonuk Chong at SKKU, and he said that, Vishal, it's fairly straightforward for them to fabricate a 100-qubit chip, but the reason they don't do it is that the tune-up times are very long. So again, I'm sure that for the audience here who are involved in building your own QPUs, this is some of the problems that you can appreciate. So what's the solution? The solution is Quantum Edge by QuantrolOx. It's our first product, and it's start of a completely new era for the fast, precise, and automated qubit control. Quantum Edge software automates the tuning and optimization of qubits. The first product supports superconducting qubits. Well, hence the superconducting, well, we are in the conference, so it's appropriate that it does that. It reduces the time for fundamental experiments such as resonator and qubit spectroscopy to a few seconds. And randomized benchmarking experiments can be done in less than 2 minutes, which, at least on our experience, is much, much faster than what we are seeing in labs and also some of the bigger companies out there. We developed Quantum Edge so that from day one, it would be useful to the community. So to be able to do that, we started to use the Blue Force lab in Delft in 2022. And we also got the control hardware from Q-Blocks, from quantum machines, from Zurich Instruments, and we were able to get the QPUs from Quantware. So in the dilution fridge that you see out there, you have 2 QPUs from Quantware, each 5-qubit sopranos, which are independently wired up to control electronics from Q-Blocks and quantum machines. And if you go to our booth, you can see the live demo. So we are doing this continuous live demo, so you can see how it works. And what we'd also like to announce now, that Quantum Edge is now available for pilot and for licensing for any of the parties out here who would like to try it out. You can see the live demo again at our booth, and also more information at the Q-Blocks booth. And I've already mentioned that we are building this with the Soprano chip, but again, the software is very flexible and can be tried with any of the other QPUs that you might have. 2 important times to remember. If you like sparkling wine, you can be at our booth tomorrow at 1:30. So that'll be, we'll have a small kind of launch event, so we'd love to see you there. And those of you who want to have a deeper dive can join the workshop. But I'm told that the limit of the workshop is only 40 people, and we clearly have more than 40 people here. So those of you who did not make it to the workshop, they can come to our booth at any time, and we'll take care of you. And before I end, my colleagues who are here today, if they can just raise your hand. Dominic, if you can just stand up, because I think from the back they cannot see you guys. So do that. Yeah. And so you can come by our booth, talk to them, and now when you're having drinks, that's another opportunity. And before I end, a big thanks to Stefan and the rest of the IQM team for organizing this event. They've been great supporters, and if it wasn't for them, you wouldn't have a chance to meet people like yourself and get feedback so we can keep building our product. Now, off to the drinks and food. Thanks a lot.
Thank you, Vishal. Thank you, Vishal. I think you said everything. We continue downstairs with a welcome reception. So the bar is open now. Enjoy the evening with some drinks, some food, and let's use this conference, what it is for communication, networking, exchange of ideas, and giving feedback. Thank you.